Alright, now we're getting into the thick of aerodynamics, starting with Chapter 4. We're going to talk about lift and stall, and do the best I can here. Hopefully, we got a good grasp now of a foundation of aerodynamics and some terminology, so we can start figuring out other more specific things, important things that happen with aerodynamics. So we'll first start with lift. Lift is equal to the coefficient of lift times the dynamic pressure times the surface area. But we can rewrite this equation as coefficient of lift times the density ratio times v squared times the surface area divided by 295. And you can see dynamic pressures in this right here in this equation. If we continue, we can rewrite this equation as lift divided by surface area divided by dynamic pressure, which you can write as 295 times lift. And we know the dynamic pressure equation is density ratio of velocity in knots squared times the surface area. So this is your equation that we're going to use in this book for figuring out coefficient of lift, or lift if you look at the last equation we had before. A lot of times you'll see coefficient of lift. We don't do calculations for these. We will get coefficient of lift from airfoils out of wind tunnels. This would be wind tunnel data, and we'll use that to calculate lift. So using the equation that we wrote before, lift CL dynamic pressure times surface area. I'm sure many of you have seen a angle of attack stall figure on figure 4.1. So if this is coefficient of lift and this is angle of attack, almost all of our airfoils have something like this, where this is CL max and this area is our stall area. And you'll see this type of graph for almost every airfoil out there if you go look up the NACA airfoils. Okay, coefficient of lift, what it is, it's basically the ratio between lift pressure and dynamic pressure, and that's what coefficient of lift refers to. If you look at page 45, we're going to do a couple of examples here. I'm using some of these equations. Specifically, if we look at writing stall speed, Vs is going to be equal to square root of 295 times lift divided by CL max times the density ratio times the surface area. So let's look at this first example on page 45. Airplane has a CL alpha curve on figure 4.1, gross weight 15,000 pounds. Wing area S 340 feet. CL max, if we looked at that airfoil on figure 4.1, is 1.3, and sea level is a standard day. So if we want to find the stall speed, we're going to take the square root 295 times 15,000. I'm just going to write 15K because I'm running out of space here on my iPad. Divided by 1.3 times 1, because we're at sea level standard day, times 340, the surface area. And this gives us a stall speed of 100 knots. So there you go. We can now calculate stall speed based on airfoil data. So you could do this for the airplane you're flying if you wanted to. You could go find the probably in the POH or somewhere in the aircraft manual, you'll find what airfoil that is for a Cherokee or Cessna, and you could go find that specific NACA airfoil, find CL max, and then what the gross weight of the airplane would be, the full fuel, the wing area, get the CL max, and for a sea level standard day, you can compute the stall speed for the airplanes that you're flying, if you so wish to do something like that. If we continue on, so we say the aircraft's flying at the same angle of attack, and we know that stall angle of attack does not vary with weight, but stall speed does. So we're looking at the second example. Assume same aircraft as above, has an approach speed of 114 knots. So this is our approach speed, airspeed. And we're still at a weight of 15,000 pounds. And we use the CL lift. It's going to be 295 times weight divided by dynamic pressure. And if we put the values in, we get a CL of 1.0. So if you look at figure 4.1, a 10-degree angle of attack must be held for this flight condition. So if the weight of the aircraft is increased to 20,000 pounds, the angle of attack remains the same, but the approach speed of the aircraft must be increased. So if we look at that, V2 times V1 square root of weight 2 divided by weight 1. And if we compute the numbers, this is 114, because that's our approach speed. This is 20,000 and 15,000. This gives us 131.6 knots. Okay? So we can see that stall angle of attack does not vary with weight, but stall speed does. And that's an important concept to know in aerodynamics. Angle of attack is also the primary control for airspeed and steady flight, so rate of climb or descent must therefore be controlled by throttle position, and that's also what this lift equation is showing us. And that's why we use throttle to control rate of climb or descent and not pitch attitude. And we use pitch attitude to control airspeed. And that's why mathematically we do that. On page 47, you're just seeing various camber effects that occur for various angles of attack for CL, and how the thickness can affect max coefficient of lift and where the airplane is going to stall. So take a look at that, and it's just going to show you basically an increase, like if you look at figure 4.3, an increase in coefficient of lift and a decrease in stall angle of attack will be noted when Okay, continuing on, we had an issue there with the Doodlecast pausing on me. So we ended up on page 46 and 47. We're going to skip boundary layer theory for now. We'll get to that later. The next important thing is Reynolds number. So what Reynolds discovered was a relationship between the point where the fluid became turbulent and three properties of the fluid stream. So if you look at Reynolds number equation, it's going to be equal to stream velocity times the distance downstream times kinematic viscosity. And Reynolds number, low values of Reynolds number is laminar, and at higher values the flow is turbulent. You'll also find in aerodynamics a good amount of information on Reynolds numbers for various airplanes and airfoils. If you look at figure 4.8 on page 51, this shows drag coefficient, so you can see laminar flow from 0.1 to 0.5, then the transition region, and then a Reynolds number of 10 and higher is for turbulent flow. So laminar flow normally exists below 0.5 million, and turbulent flow exists for values greater than 10 million. Okay, I'll write that here. RE 0.5 is laminar, and RE of 10 or greater is turbulent. And we base this off a flat plate. Skipping ahead, we look at page 53. It's going to tell us the definition of stall. Stall is airflow separation of the boundary layer from a lifting surface. It's characterized by a loss of lift and an increase in drag. Pretty straightforward. High coefficient lift devices. On page 54, talking about the plane flap, split flap, and leading edge flap. And probably, as most of you know, all these devices are there to enable an aircraft to take off and land at reduced speeds. That's what we call them, high lift devices. Those are maintaining that pressure distribution accurately across the airfoil to increase the aerodynamic force, to decrease drag, and to allow the airplane to lift off the runway without having to go extremely fast and various other reasons. So the flaps also help us with slowdown. So as we're coming in to land, when we dirty the airplane up and lower the flaps, we are going to increase lift and increase drag. So that's basically all we're saying here with the various aspects of lifting devices. So take a look at some of that. And I think this is it for chapter 4. Okay? Let me know if you have any questions. Thank you.